In this video, we're going to be talking about first-order differential equations that are linear. Okay, what is a linear first-order differential equation? Well, as you can see, a linear first-order equation can be expressed in this form. So here you can see we have a function of x only multiplied by dy dx, a function of x also multiplied by y, and that's equal to a function of x. So as you can see, for a first-order linear differential equation, the dependent variable y and its derivatives so of course that's y and its derivatives appear in additive combinations of their first powers. So let's take a look at two examples here. Taking a look at this first example, let's go ahead and write that left-hand side, the sine of x multiplied by dy dx plus cosine of x multiplied by y is equal to x squared multiplied by the sine of x. So as you can see here, we have a function of x multiplied by dy dx. We have a function of x, which is cosine of x. And here is our function of x on the right-hand side. So this is a linear differential equation. But looking over here on the right, can you see this y cubed? And also, we have y multiplied by this. So this is not first power of y. And secondly, we have a multiplying of our dependent variable by its derivative. So that must be additive, not multiplying. So this is non-linear. Okay, so let's talk about how we're going to solve a linear equation. So the first thing we want to do is isolate that derivative term. So you can see we have dy dx, and then we will have some function of x multiplied by our dependent variable y, and we will have a function of x on the right-hand side. Once we come up with that form, this function right here in front of that y, this is going to be very important. We are going to define mu of x is equal to e to the integral raised to the power of the integral of p to the x dx. So our first job, we will need to find the integral of p of x dx. And then, of course, we will define mu of x as e to the integral of p to the x dx, okay? And what you will notice is after we multiply the equation by mu of x, so we will multiply both sides by mu of x. What you're going to find is that left-hand side is simply going to be the derivative of mu of x multiplied by y. This is the chain rule. And the derivative that's there is write the function times the derivative of the second function plus the second function multiplied by the derivative of that first function. So you can see it right here. So that left-hand side is going to be the derivative of mu of x times y. And the right-hand side, we will have mu of x times q of x, okay? And q of x was that function on the right-hand side when we wrote that in our standard form. And then we will integrate this last equation and solve for y by dividing by mu of x to obtain this solution. So to obtain y of x is equal to 1 divided by mu of x multiplied by the integral of mu of x multiplied by q of x dx plus a constant. See if I can move that over just a little bit. So that's our goal, is to obtain y. Okay, let's give this a try. We have this first order differential equation here. And for this example, we're going to go ahead and multiply every term by x. So we'll have dy dx minus 2 over x multiplied by y is equal to x squared cosine of x. So now we can see here what p of x is equal to. So as you can see here, we have p of x is equal to the opposite of 2 over x. So we will integrate p of x dx, which is the integral of the opposite of 2 over x dx, and we come up with negative 2 multiplied by the natural log of the absolute value of x. So therefore, mu of x, remember, it's going to be e to that integral, which is negative 2 multiplied by the natural log of x. Now, we're going to be able to simplify this, and we can actually write this as e to the natural log of the absolute value of x raised to the negative 2 power. And since x is positive, we can go ahead and take those absolute values off and just write that negative 2 there. And let me go ahead and write since x is greater than 0. So now that is our mu of x. Therefore, mu of x is equal to x to the negative 2. So now we're going to go ahead and remember this is our standard form. So we're going to go ahead and multiply our standard form by mu of x. So we're going to have x to the negative 2 times dy dx minus 2, and now we will have x to the negative 3 multiplied by y is equal to the cosine of x. Okay, so now this is what we end up with. And here, and I should have had just an x cubed here. And we can write that as x to the negative 2 dy dx minus 2x to the negative 3y is equal to the cosine of x. So now what we want to note is that this right here on the left-hand side, that is actually equal to the derivative with respect to x of x to the negative 2 multiplied by y. And so that is equal to the cosine of x. So now we're going to go ahead and integrate both sides. So as you can see, we have x to the negative 2y is equal to the integral of the cosine of x dx So we have x to the negative 2y is equal to the sine of x plus a constant. And solving for y, we have x squared sine of x plus c times x squared. Here we have our general solution. There are infinitely many solutions, one for every value of c. So as you can see on the right-hand side here, we have sketch solutions for various values of the constant c. You can see c is 1, c is a half. All of those are for this c value. Okay. Our next example, a rock contains two radioactive isotopes, Ra1 and Ra2, that belong to the same radioactive series. That is, Ra1 decays into Ra2, which then decays into stable atoms. So we are going to assume that the rate at which Ra1 decays into Ra2 is 50 e to the negative 10t kilograms per second. Because the rate of decay of Ra2 is proportional to the mass y of t of Ra2 present, the rate of change of Ra2 is. And you can see here that we have the rate of creation minus the rate of decay. So here is our differential equation. This is going to be a linear dE, and let's go ahead and write that linear dE in standard form. Okay, so also note that we have K is equal to 2 per second, and so we will go ahead and write dy dt equals 50 e to the negative 10t minus 2y. Now, let's go ahead and work that below. So we have dy dt is equal to 50 e to the negative 10t minus 2y. By the way, we do have an IVP, we have our dE, and we have our initial condition, and we are going to be finding the mass y of t for Ra2. Okay, so let's go ahead and write our linear dE in standard form. So in order to do that, we will bring the 2y term over. So we have, dy dt plus 2y is equal to 50 e to the negative 10t. So now we have standard form. Okay. We can see that p of t is equal to 2. You can see it right here. And so we have the integral of p of t dt is equal to the integral of 2 dt, and that's equal to 2t. So now we have mu of x is equal to e to the 2t power. So now we will go ahead and take our standard form, which is right here, and we will multiply both sides by mu of x. So we will have e to the 2t multiplied by dy dt plus 2e to the 2ty is equal to 50 e to the negative 10t multiplied by e to the 2t And we're going to go ahead and combine these in our next line. What we notice right here is this left-hand side is the derivative with respect to t of e to the 2t multiplied by y. And one thing you might want to remember is that this e to the 2t is in front of our dy dt term, and this is always going to be y. Okay, so it's not too difficult to see, to write that left-hand side. And here we have 50 e to the 8t, negative 8t. Okay, so now we're going to go ahead and integrate both sides. So we have e to the 2t multiplied by y is equal to the integral of 50e to the negative 8t dt. And we have e to the 2ty is equal to negative. And so what we notice here is we will have 50 over negative 8. So we'll have 25. So we have minus 25 fourths e to the negative 8t plus a constant. Let's divide every term by e to the 2t. So we have y is equal to negative 25 fourths. And if we're going to divide by e to the 2t, this will be e to the negative 10t plus ce to the negative 2t. So that is our general solution. Of course, we need a particular solution. So we are going to use our initial condition, which was y of 0 is equal to 40 to find c. And so doing so, we will have 40 is equal to negative 25 fourths e to the 0 power plus c e to the 0 power. And as you can see, we have 40 is equal to negative 25 fourths plus c. I'm going to go ahead and just make all of this just a little bit smaller so I can have some room here. And so if you go ahead and take a look at that, we will have c is equal to 185 divided by 4. And therefore, y of t is equal to 185 over 4 e to the negative 2t minus 25 over 4 multiplied by e to the negative 10t. And of course, we still have that t has to be greater than or equal to 0, which was noted right here. Okay, and this is our particular solution, the solution to the IVP. Okay, let's look at our next example. For the IVP, we have here, this is our differential equation, and this is our initial condition. And we are wanting to find the value of y of 2. So we will have to come up with our particular solution first. Sometimes we run into an issue finding that indefinite integral on the right-hand side. Let's see what this problem brings us. So we will go ahead and proceed and see that we are already in standard form. So this is the standard form of a linear DE. We are already in standard form. And as you can see, P of x is equal to 1. So mu of x is equal to e to the integral of 1 dx, and that's just going to be e to the x. So now we will go ahead and multiply both sides by that. So we have e to the x dy dx plus e to the xy is equal to e to the x times the square root of 1 plus the cosine squared x. As you can see, this right-hand side is the derivative of e to the x multiplied by y. And then now we have to integrate that right-hand side with respect to x. And now you can see that we have e to the x multiplied by y is equal to, and now we have a difficult time with this indefinite integral. So basically what we have is the ability to use definite integration. So let's go ahead and write below this that we cannot express in finite terms. But we can use numerical algorithms such as Simpson's rule, things like that. So we are going to use definite integration. From x equal 1 to x equal to 2. And you can see here x is equal to 2 and x is equal to 1. And this is what we're looking for, and this is given. Okay, so let's go ahead and give this a try. So we are now going to have that left-hand side, and this was not supposed to have that on there. And so now, since we can't do that, we are going to go back and use that form. And so we are going to use definite integration. And so we will have e to the x, y evaluated from x equal to 1 to x equal to 2 is equal to the integral from x equal to 1 to x equal to 2 of e to the x multiplied by the square root of 1 plus cosine squared x dx. Now, this left-hand side is e squared y minus ey, and that's going to be equal to, now keep in mind that this is y of 2 and this is y of 1. So we do need to keep that in mind. And here we have that right-hand side is just the integral from 1 to 2 of that same expression. Okay, and so now if we want to go ahead and solve for y of 2, and let's go ahead and just have that here, we will go ahead and have e times y1 plus the integral from 1 to 2 e to the x 1 plus cosine squared x dx, and then dividing all terms by e squared, we have y of 2 is equal to e to the negative 1 multiplied by y of 1 plus e to the negative 2 multiplied by that definite integral. Okay. And now let's go ahead and substitute our value of y of 1. And remember that y of 1, was equal to 4. And so we have y of 2 is equal to 4e to the negative 1 plus e to the negative 2 multiplied by that integral from 1 to 2 of e to the x, square root of 1 plus cosine squared x dx. Using a calculator to compute this, you will come up with this definite integral is 4.841. And so we have y of 2 is approximately equal to 4 over e plus 4.841 divided by e squared. And that is approximately 2.127. Therefore, y of 2 is about 2.127. Let's take a look at this existence and uniqueness of a solution. So theorem 1 tells us that if p of x and q of x are continuous on this open interval AB that contains the point x naught, then for any choice of the initial value y naught, there exists a unique solution y of x on this entire interval to the IVP shown here. So it's pretty powerful. In fact, basically it says that we have the existence and uniqueness of the solution on the whole interval. So we have existence and uniqueness of the solution on the whole interval AB. Okay, that concludes this section.